Okay, Prof, I think we can start the lecture today. Uh, all the students, I think, already joined with us here. And before we start, probably I will try to open the guest lecture today officially.
Okay, Dr. Jamal,
Okay, can we start? Yeah,
yes, but I need to see the people, the room, the students, so that I can know how to talk to them.
yeah. Okay. Probably to all of the students, if you can try to open the camera, it is good. But if you have a problem with the connections, it is fine. You can just try to switch off the video. Okay. Okay.
Yeah,
Can we open officially the lecture?
yeah, it's fine.
I will try to introduce. Okay. Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Uh, dear Professor Picho Ingoy Bokalombe, and also all of the students who are attend this guest lecture. Thank you very much for your time to have today, and especially for you, Professor Picho. It's our honor to have you here with us uh, to give some to, to my student here. Before we start the lecture, our guest here today, uh, Professor Picho Enggoy Bokolombe is from University of the Kinshasa, Department of Chemistry. Uh, and also, if we have look the academic record of him, that he obtained the bachelor and master degree in 1995 until 2002. And also, he obtained the PhD degree in chemistry in 2012 at Masaryk University under supervision Professor Peter Klan. With the special topic is about the study of photoreaction mechanism of photoactivable compound. And in addition, he also do some postdoc fellowship, especially at 2016 until 2018 at the Rhodes University under supervision of distinguished Professor Hebelo Nyokong, and also research stay here in Kansas University in 2011, and also at Masaryk University at 2018. And in September 2022, he obtained a full professor at the University of Kinshasa. And according to his publication record, he already published a lot of publication in a really good journal. And especially in 2021, he already published in Nature Materials, which is well known as the high impact factor journal. And instead of Nature Materials, he also published many articles, uh, let's say in New Journal of Chemical, and also Frontiers in Chemistry, and also diagnosis and photodynamic therapy, and etc. So if we have a look to the topic of his research, mainly he reported many things regarding the transient absorption spectroscopy. So we believe that he is the expert of this transient absorption spectroscopy, especially for us who are dealing with the organic reaction mechanism. So it is my honor to have you here to give the students some introduction to this topic. And for you also, what we have here, the students are from the bachelor and master degree, not only from Pajajaran University, but also from University of Jambi. This is outside or different islands, which is from Sumatra. So, and before we start the lecture, I would like to remind the student that the student can ask the questions during the lecture by typing in the chat box, or the student can also ask directly later on at the end of the lecture during the discussion sessions. You can ask either in English directly, or you can also ask in Bahasa, and then I will translate for you. And the last, there is an assignment also for the students to have or to write some summary after this lecture about the transient absorption spectroscopy. And then you will have to collect later on as the assignment. I think that's all what I can explain before we start the lecture. So please, Professor Picho Enggoy Bokolombe, you have your time to deliver the lecture.
Thank you, Dr. Jamal, for the opportunity. Thank you for collaboration. And I will try to introduce the transient absorption spectroscopy for the study of organic reaction mechanism to your students in your university. As we said, I used this technique for more than 5 years, so I can't show everything. I will just show the introduction in order to introduce the student to this method of science. So I will start my lecture by showing some examples, and then the curiosity of the scientists, especially the chemists. And here we are in the excited state. So it's like they can see we have the para-hydroxyphenacyl moiety. Is commercially available. We can buy it, then do whatever you want with it. But we just realized after irradiating this compound, we had it in our hand, and then what we isolate is these two compounds, para-alcohol, benzylic alcohol, and then para-hydroxyacetic acid. The second example is we took the same compound, but we cyclized. X is a living group, which can be diethyl phosphate, tosylate, mesylate, acetate, or whatever kind of ester. But when we irradiate the compound, what we isolate is what you see, these two compounds. And then the third example is this one. We irradiate this nitrophenacyl group containing the living group in hydrogen donor solvent, and then we got the nitroso compound. What's going on in between? This is the curiosity of the chemist in order to decipher and to establish a completed mechanism. The fourth example is this one. We use phenacyl xanthate. Radiate in acetonitrile, we got the recombination compounds product. And then when we radiate in hydrogen donor solvent like 2-propanol, we have phenacyl, and then carbon sulfide, and alcohol. Then we said, what's going on inside, in between the reagent and the product? So to know what's going on in between, and then to write or to propose a mechanism, we need some ultra-fast device. We need some ultra-fast spectroscopy in order to probe the transient. So when we probe the transient, we have to show is absorption spectra. That's why we call it transient absorption spectra. And then we have to do kinetic or kinetics to show the lifetime of the appearance of this species and the disappearance of the species in order to propose the completed mechanism, which can lead to understand how the product was formed. Before explaining these 4 examples, I will just pour some theory in order to remind people where we are. So in general concept, I can show there is a scale, different time scales, and what was going on inside. From giga to etto, we don't care, but in transient absorption spectroscopy, we care from micro to femto, which have now devices to control everything. But because we know that from flash, we can talk about milliseconds, but from transient spectroscopy, we talk about nano, pico, and femto in order to generate the intermediates and to show their UV where they absorb at this transition state. And then this relates to kinetic, which will call us to remind about Arrhenius equation, Airing equation, to know the rate constant. But in general, for the theory, it's known like transient spectroscopy. It's very similar to the normal spectroscopy, UV, what we know, which is electronic transition. But in transient spectroscopy, the species are not stable in excited state. And like they are not stable, the lifetime also is very short. So we need some device to pump, to generate, and then to probe the spectra to know how it absorbs, to know the lifetime of appearance and disappearance. But for the slow reactions, we don't need transient spectroscopy. We need just the normal spectroscopy. We can use UV spectrophotometer. But for to probe the fast intermediate and then to show them in order to propose the mechanisms, we need some techniques. So what's going on in transient spectroscopy? So we know if we irradiate the compound, it goes from ground state to excited state, which should be and must be singlet. And then the transient spectroscopy will bring, after stimulating the light, it will bring now the excitation upper excited state. Then when it goes to intermediate, we have to see the intermediate appearance. We have to see the intermediate disappearance. So to do that, we need what we call a laser. The role of the laser, which is an acronym, laser is acronym, which is light amplification by stimulated emission of radiation. The laser is there for generating what we call intermediate or transient species using whatever, maybe continuous wave or pulsed, and then the probe will just capture the spectra in one wavelength, using monochromator. We will see it later. The monochromator will help us just to monitor in one wavelength. Then if we want to get it more, then we will use the CCD camera to have the more than 1,000 spectra of this species in that place. Then we will do what we call deconvolution of the spectra to see where the singlet it absorbs, where the triplet absorbs, the biradical absorbs, the radical absorbs, and to see all the fast species, to know their lifetime, and then to write the mechanism. But before going there, we will start what we call Because in normal kinetics, we used to say about steady state kinetics, or the constant of the intermediate, or the concentration of the intermediate is constant. But what we do in transient spectroscopy is time-resolved spectroscopy. But in steady state, the light is used, which is used is like one wavelength with using like solar simulator or UV spectrophotometer. You can follow continuously by irradiating what you need until you reach the constant concentration, and then this facilitates the measurement of the weak signal. And then you can get from these calculations, I can just recall students about complex kinetics, which are many, many steps. So in each steps, you have one rate constant. And then this facilitates the calculations to have for all the reaction different lifetimes or different rate constant. And then steady state spectroscopy are the best if the measurement of absorption or the emission are done without any problem. But time-resolved spectroscopy uses two kinds of light: the pump and then the probe. The probe light is continuously shining like in steady state, but the pump is coming using pulse laser. And then this pulse laser is very powerful. That's why we say the time-resolved spectroscopy rely on the irradiation sample with a light source whose intensity fluctuates as function of time. That's why we call it time-resolved spectroscopy. So if it's done like that, the laser will flash, and then the light flash creates a burst of excited state whose evolution can be monitored as function of time. That's why we said in time-resolved spectroscopy, we can provide kinetic information, and then even if the compound is very low concentration or very low sensitive, we can compare it to steady-state techniques. Then, what is the pump probe now approach? I can say all the books in physical organic chemistry talk about the techniques of pump probe, but all the techniques allow in general to study what I said before: the disappearance of the excited state, the formation of the reactive intermediate, and also the formation of the product. If you have all those stuff in your hand, then you can you can propose a mechanism with proofs. But here I didn't put the equation. I didn't want to put kinetic equation. It's just introduction. So theoretically, what is going on is when the absorbance changes with the selected wavelength, we can talk about kinetics. But when you have several wavelengths simultaneously, we can talk now about transient spectra. But this method referred to pump probe, what we called before, and then it used to be perpendicular. It's like the probe is irradiating straight continuously, and then the pump is pumping perpendicular to the probe, to the sample. But the pump is not pumping, is not flashing continuously. It's just one flash, which can destroy even the compound, but at least and it will bring the compound in excited state, upward excited state. And then from this excited state, the probe will capture the UV spectra of this compound in that upward excited state. And then the time also, the upper will come ground or will go to intersystem coursing to another state. And then you know that I think Dr. Jamal told you about this. In singlet, you have the spin, which is anti-parallel, it's normal, but in triplet state, because of intersystem crossing, all the spin are looking the same side, like parallel. So in that case, if it want to come to phosphorescence, or in the triplet state, we have it like parallel, the same size, but in the ground state, which means phosphorescence, it should be changing again to the other side. So these techniques allow to probe all those intermediates in that way. But as chemists, we know that the pump laser excites the sample, but it's the researcher or the chemist who will fix the wavelength according to the normal UV spectra of the compound. It's like you take the normal UV spectra of the compound, and then you know where it absorbs, then you will quietly set the wavelength to monitor in the place the compound is absorbing. But be careful, don't flash in the maximum, which is not good, because in the maximum, the laser will just destroy the compound, and then the study will not be allowed to make it to be made kinetically. That's why the laser pulse width must be much shorter than the rate constant of the reaction when you are doing. So the probe beam should be broadband. It can be UV light, it can be invisible, or in the NIR, the same thing in that range, so that the transient electronic transition will occur in that place. Normally, they use different source, continuous wave, which we call CW, or pulse length for nanosecond, or even longer scale, you can go to femtosecond or millisecond anytime. But what's going on in that case, when you set up everything, the experimental parameter of interest will change the absorbance of the sample. And then from the change, you will calculate the transmitted light intensity of the probe beam before the laser excitation and after laser excitation, according to this small formula. That's why in all the transient spectroscopy, or in all the transient spectra, we used to write change in absorbance, because it's not only the absorbance, it's the change before and after the laser excitation. This is why the way we use it. And then we can change different scales, but what is the use of the transient spectroscopy? What is the importance? What is the problem chemists want to use transient spectroscopy? There are more than 5. I just choose 5 in order to show how it's going. First of all, the chemists want to identify reaction intermediate from their spectral feature. This is the first one. Second, the chemists want to assess the reaction mechanism by detecting spectrally distinguishable reaction intermediate. And then the chemists want also to determine the rate constant of each kinetic step. And then fourth, you want to determine activation parameter, especially using Arrhenius equation, from the temperature dependence of the rate constant. And finally, you want to determine reaction quantum yield in favorable cases where extension coefficient of the reaction intermediate are known. And it can be known only using normal UV spectroscopy. This is the reason why the chemists want to use transient absorption spectrum. Some of the reasons, because there are many. So now we will be going all the range, as I said from the previous slide, from millisecond to femtosecond. So when we are in millisecond, you can use even the flash from photo device. You can use your cell phone just to use by to use a steady-state spectrophotometer, which can be using normal, because the reaction is very slow. And then the spectrophotometer will follow one after one, the absorbance at the wavelengths at function of the time, providing a kinetic time course for the photo-induced reaction. But when can we use this steady-state spectrophotometer? Only when we know that the time constant is in the range of minutes or even longer. But if the species is very fast, just forget about this method and then think about the other one. The other one can be now from microsecond to nanosecond. That's why I said for the faster reaction, we can use the multi-channel detector charge coupled device, which we call CCDS, or you can use photodiode array, which are used to follow just the time evolution of the absorption spectrum. So if you use, in that application, you need continuous wave broadband light source so that you can easily probe the absorption spectra of the sample. But also, if you don't need one wavelength, you can use 2, 3, 4, even more. That's why we call it polychromatic beam. They are there. You can use filters to do whatever you want, or just remove the filter and put just quartz and leave everything to go. That's what we call polychromatic. It will pass through the spectrograph. Then the absorption spectra will be monitored as function of time. And then there are many setups according to the industry, and then the country. Many specialized setups are also there to select wavelengths, but especially monochromator, they are now digital to fix the wavelength we want to do. Then these are the illustrations of photodiode array and the detector, the CCDS. It's a typical optical layout for absorption spectrophotometer. In left, you have diode array spectrophotometer. What you can pay attention is, for the diode array, you have, after the source of light, you just have your sample, then slit dispersion device, so you have everything after the detection. But for the CCDS, you don't have the sample in front of the source. You have, however, you have entrance slit, the prism for the dispersion device, you have the exit slit, then you will have the sample. After the sample, just you have the detector. That's why we call it a single detector spectrophotometer. And the amount of light transmitted is detected one wavelength at one time. This reminds us the second law of photochemistry. So, from millisecond to nanosecond, as I said, the device will change because we use now flash photolysis. And then flash photolysis, we'll see later on, we'll do the same thing using pump and probe. But the change in absorbance will go from millisecond to nanosecond according to what we want, and then how speed are or how fast are your intermediate. Because if you have an intermediate which can be seen and disappear in femtosecond scale, but you are using milli, micro, or nanosecond, it means just you won't see nothing. You won't see anything. It's like, okay, I didn't see anything, so the intermediate is not there. No, you have to go all the ranges, then you may know if it's very fast, then femtosecond. Because the absorption of light, 1 quanta of light, is like 10 to minus 15 seconds. So it's very fast. And then if it's more than that one, we use just to say, okay, it's faster, and then singlet oxygen is not seen or not, and we will see later. But the fast shutter exposes the sample to the probe beam shortly, just shortly before the laser pulse hit the sample. Because if you leave the shutter, you didn't shutter the sample, the continuous light from the probe, it will just destroy the compound, and then the measurement will be tracked. So after flashing, you have to close the shutter. And then after opening, you have to flash, and then the sample to probe shortly, because in that case, if you don't close, everything will be destroyed. And you have to avoid what we call in photochemistry, photo bleaching of the sample, which means the kinetics is just gone. So from millisecond to nanosecond, there is microsecond in between. That's why when you are using nanosecond, it's good to see microsecond. But when we are using a millisecond to second, no way to see species which are in microsecond. That's why we don't put microsecond in between, but we know that it's there. From millisecond, nanosecond, there is microsecond, and there are devices for all three. And then what I was saying is here now the illustration. Here you have the laser, which pump the light, flash after flash. Here we have the shutter, then the sample. The lamp is for the probe. The probe is here continuously irradiating, but it can be hidden when you put your shutter, protect your sample. But don't flash without opening the shutter. You have to open the shutter and then flash, and then after flashing, you close the shutter to avoid the destruction of your compound. This is the way I told you it should be perpendicular. You see the probe is there continuously shining, and then the pump is just after flash, you see what happened. That's why we said this, it's kind of a nanosecond laser flash photolysis setup where the lamp from the probe can be like xenon lamp, mercury lamp, or just a solar simulator lamp, which can be xenon or mercury also. Not arc lamp, but not mercury. If you have it in that case, so you have the kinetics. The decrease of the kinetics means the disappearance of your species. If there is another species coming after disappearance of the previous one, normally you will see the appearance of the new one. Once the previous one is disappearing, you will see the appearance of the new one. If it disappears until it reaches zero, then there is nothing coming after that. So in that case, you will just show the time profile of the probe light, and then you see the change in intensity. But if nothing is starting yet, you have like you don't need about the slope. You have just to say what the machine or the device will tell you. So the change in intensity induced by the pulse laser will be highlighted, and you during the experiment, you may know at which time I can set my reaction. So for the polychromatic, the same from the sample. You see the CCD camera for the spectra. This spectra, as you see here, is just the convolution of many spectra, one. And then this is the kinetic decay of one of the time monitored using the wavelength, the wanted wavelength. That's why I said the wavelength at which the reaction kinetics are monitored or to measure transient spectra must be a function of time. This is the common time-resolved spectra of the carboxy hemoglobin. So just an example. If you see here, this one spectra, and when I come here, it's like most of the spectra were there. After the convolution, I get one. It's one. This is the spectra of carboxy hemoglobin, but this is in 3D. As you can see here, the change in absorbance. Here you see the time. in second, and then you can see it's time until 10 to minus 6. And then here you have it in wavelength. This is 3D spectra of carboxyhemoglobin. It's an example to show. And then the kinetic is here. Kinetic decay of the carboxyhemoglobin is there, monitored with wavelength only 1. So when we go to sub-nanosecond domain, which means above very fast kinetics, the pump, instead of using one pump probe, both of them are using in the same time, so there is no perpendicular at all, but we use now a detector. That's why we said, when the absorbance changes are to be monitored in sub-nanosecond, the probe beam is obtained by second broadband laser pulse. The pump is coming here with the same spectra. The probe is taking the spectra, sample is there, and everything is seen in using the detector, which are most of the device digitals. We can use all the software to have them. And then after nanosecond, we have picosecond and femtosecond, which we have the device up to now. Up to now, we have the device until femtosecond. Atto, not yet. People who worked with this are there. You can Google them and see they did. You can just Google them. The previous one for the microsecond and millisecond range was Mr. Hagen. Then for nanosecond, microsecond, and nanosecond, it was about Norrish and Porter, which they got the Nobel Prize at 1967. And then for femtosecond, it was Ziwal, who passed away, I think, two or 3 years ago. He's from Egypt, but he worked in the US, and then he became American. He's the one who built the first setup of femtosecond. I think he passed away 2 years ago, Ziwal. And the scale of generating transient species starts from millisecond, microsecond, nanosecond, and femtosecond up to now. In our laboratory in Czech Republic, we use both of them. On left, you can see this is millisecond until microsecond. Nanosecond is not here, but this in green is the femtosecond one, which can take also picosecond, from picosecond to femtosecond. So the principles are the same. You have your sample here. The continuous light source, which means the probe, is there. And then the laser will come with the pump. The wavelength was already monitored using monochromator. The photomultiplier will just conduct the digital transient to have the kinetic decay after analysis. For micro, milli, and nanosecond is the same. But for the femtosecond, it's not the same. On the femtosecond, we have a garnet, yttrium aluminum garnet. This garnet shine light at 1054 nanometers, which can split it to 2. You will have like 530, which is in green color in the laser, which we can see there. This is the second harmonic, just divided by 2. You have it like in green color. Then it can be changed if we divide by 4 or 3 to 355 or 266, according to the UV absorption spectra of your compound. You have to start by getting the normal UV to know where your compound is absorbing. Then you can fix and monitor which wavelength you wish to start kinetics studies or to have the spectra of transient absorption spectroscopy. And I will start to say like about the probe beam. If the garnet absorb or shine light at 1054. No way to, there are mirrors in that setup which can split the beam time to time. And then you have now the kinetic information after the convolution of the spectrum. But like the probe is continuously shining as function of time, you will now the delay of the pulse to set up the time resolved spectroscopy in order to have the kinetic information, in order to know the wavelength, because the UV spectra, the normal UV spectra is not the same compared to the transient UV spectra. No, they are different. But normally you start by knowing the UV spectra so that you can fix the wavelength from there, knowing that after shining the light, the intermediate will come with its own spectra, which will not be the same. It's very, very rare to see this, the excitation and the emission the same place. No, one used to be the mirror of the other. But in that case, it's like the compound is in excited state, the probe takes just its UV, which will be different compared to the UV in the ground state. And then now I can try to explain after theory. I don't know, Dr. Jamal, if there is question, or I may continue to explain now one example after one mechanisms.
Yes, I think just continue first, and then we will open the discussion at the end.
Okay. So I will try to respond to the first question. When we have phenacyl group, then in our hand we isolated acid group or carboxylic acid and also alcohol. What did we do? We know that we have phenacyl group in our hand, and after irradiation we have this carboxylic acid, and then this alcohol in our hand. What's going on? What was the mechanism in between? So we use ultra-fast laser, knowing that the compound after irradiation, it goes through the singlet state. And then we have to prove where this singlet state absorbs, what is the spectra of this compound at the singlet state, and then what is the lifetime of this singlet state. And then when this singlet state disappears, is the triplet state coming or not? Because there are some reactions which stops just in singlet state, then you have the product. So before claiming that there is triplet state, you have also to see where the triplet state absorbs. And then you have to know the building lifetime of the triplet and the decay of the triplet. This is what we did. We can see the singlet state is here. Then after running femtosecond laser probe, we see there is a band here around 350, between 350 and 300 nanometers. Then the lifetime was very short. Then we realized the disappearance of this band. Then meanwhile, the disappearance of that one. You can see the kinetic here, decay of the singlet, the building up of the triplet in femtosecond. Then we said the singlet is here in red. And then the triplet starting to come up here in green. And then the triplet of what? Is it the triplet of the compound or the triplet of ion pair, the radical of what? So we said, okay, let's make some measurements, see the rate constant of the intersystem crossing. Then we realized, because the reaction was done in water, we realized that this was the triplet of the phenacyl group when it didn't release the X, which means the living group. So we realized the triplet, when the singlet was disappearing, the triplet was coming here. You can see this triplet better here, where the singlet is almost gone. There is no singlet, and you see the triplet is seen there like a rainbow. So when the leaving group is gone, meaning like there is something remained here, but there was water. So what did we say? We have to think about this biradical, this triplet biradical, because the leaving group here is gone. Then the radical here and this one is a triplet biradical, which will be detected later on, we will see, using another molecules. But this is just a suggestion. We suggested that this must be like that, so that we can think about the Favosky reaction for organic chemistry. You know Favosky reaction, but like if it's done here using light, we called it photofavosky reaction. Just to remind you about the alloalkane, cycloalkane with Favosky reaction. Then you will see this cyclopropanone here for Favosky. Then after ring opening, we had the carboxylic acid. This was the first suggestion, because from the singlet, we saw the spectra, the kinetics. Triplet, we saw the spectra, the kinetics. Then the radical was here, thinking about the departure of the proton, the hydrogen, of the hydrogen, then the cyclization of the photofavosky reaction. So the ring opening, because when you use water here, because it was water in the solvent, when you use water here, it will give you, the ring opening will give you carboxylic acid, which we have in our hand. The same thing, if you have this cyclopropanone coming from photofavosky reaction, then you just decarbonylate, you have a quinone. If you decarbonylate this cyclopropanone, you have a quinone here. So the quinone is like, there is ethylene close to here. So remember that when we hydrolyze alkene, it will give us alcohol. That's why we have benzyl alcohol here. And the benzyl alcohol and the carboxylic acid were isolated after irradiation or the phenacil. So we were allowed to write a completed mechanism and publish. To confirm the presence of this quinone, we use IR. Then the vibration band of carbonyl group was here to confirm this quinone, and then the double bond from the aromatic was there. This is carbonyl group, and then this is the double bond for the IR, and we confirm that, okay, the quinone was formed also during irradiation, and then like irradiation was done in water, you have benzyl alcohol. This was the first example. We established the mechanism and published in Journal of American Chemical Society. So the second one, when we saw that, said, okay, let's try to cyclize this phenacyl group using different CH2 to see what will happen. So what we did is, if you remove just these two, we have phenacyl group. We just put cyclize in that place. Then we put the bad leaving group, which is acetate. It's a bad leaving group. And when it will leave here, it will be acetic acid, and then you know the pKa of acetic acid. We try now to probe the UV spectra of this compound in excited state. Then we realize, no, okay, if the compound is neutral, the UV absorbance in excited state, transient absorption spectra maximum is around 250 nanometers. And then if we deprotonate by putting a phosphoric acid, then we have an ion. Even in water, it can deprotonate. And we see out of this band, which is closer to neutral one, there is another band coming here around 400. And then when we did the kinetics, we just realized it was not the same. It was different. Then we said, okay, this is for the quinone, which we call triplet quinone E, and then this the red before it's for the anion. We just published in Journal of Organic Chemistry this result, along with the other one. This was the groundbreaking work. When we use this, previously we were thinking about this biradical, triplet biradical, which was not seen. It was not seen. It was like doubting because it was closer here. Then here around 350, the publisher said it should be like there, but no one could believe, but we just proposed as a mechanism. But when we changed to cyclize, we got this one in that place, which is almost the same. And then after irradiation, the band which was this one, this band, 400 is here. Another band comes close to 400, is at 450, which were signed to be triplet biradical. In that case, if you remove this one. But for the phenacryl group, it was in confusion between 350 singlet and biradical. But the triplet radical, when we cyclize the compound, it became easy by using now the good living group, which was mesylate. Because acetate is bad living group, mesylate was a good living group, and it shows us the triplet biradical. Then also, we isolate the compound. That's why we published in Journal of American Chemical Society, because this was novel. This biradical, triplet biradical was novel. People were just doubting about the existence of that, because from this, then you have Photo-Favosky reaction. Out of this biradical, there is no Photo-Favosky reaction. Then we go to propose this mechanism. From the triplet, because we know there is singlet already is known, from the triplet state now, the reaction goes through the formation of triplet biradical. After intersystem crossing, you have now the Photo-Favosky reaction with this cyclopropanol. And then like the reaction is done in water, we were able to isolate after irradiation, isolate this carboxylic acid compound. The same thing from here, when we decarbonyl, we remove the carbonyl group. Then the same thing like we saw in the quinone. Then in water, you have again the alcohol. If you remove just this 1 and 2, you have still the benzyl alcohol as the previous one. Then when we do everything is in water, we can get this one after isolation. The same we published the same year in Journal of Organic Chemistry. So the third one was this monochromophoric linker. We are able to see this compound, then to isolate the nitroso. From nitro, we isolate nitroso, and then the carboxylic, the ester will became acid, the ether became alcohol using hydrogen solvent donor, and then acetonitrile. But what we did, we synthesized a compound like this one, starting by nitrophenacil. We irradiate. We went from singlet to triplet state, intersystem crossing, but we realized we have nitroso as compound isolated. We started by nitro, and we end up with nitroso. None of the atoms was out, a part of the living group, which became acid. Which mechanism can lead to this? And we started by talking about acinitro. We put the solvent here after in the triplet state. We saw the acinitro as a neutral, and then we saw also the acinitro in an ionic form after putting water or just 1 millimolar of sodium hydroxide. Then we said, okay, we see the species, we think about the species, we have to see them to confirm the existence of all the species. Then we start now with nanosecond laser. In red, you can see it's the transient absorption spectra of the acinitro neutral form. This OH will just leave and the oxygen will remain. And then 9 seconds after the flash, as I said, the time should be shorter. So when we push the time to 220 nanoseconds after the flash, then we saw this species, which was already published before, at the same place, 450 nanometers. Then we decide to change the different, to put it in different solvent to confirm it's acid-nitro, neutral one. We put it into the compound in water or in 1 millimolar sodium hydroxide, it will move because of the pKa of the compound. It will move, it will redshift. So we just put the compound in water, we realize the deprotonation, and then the spectra move. We confirm that at 450 is acid-nitro, and then 530 it's also acid-nitro, but deprotonated. So you can watch this table. These are the lifetimes, the kinetics. Those are just the spectra, but to confirm the lifetime of the species, we have to shift it to kinetic mode. We measure in acetonitrile, in methanol, hexane, water, and then sodium hydroxide. You can see it's very slow in water and sodium hydroxide just because of deprotonation. And then acetonitrile, methanol, hexane, the lifetime is almost the same. And then this was done out of oxygen. We just removed oxygen in the solutions to avoid triplet annihilation. And then the wavelength, the monitored wavelength, the fixed wavelength using monochromator are here. 450 for the three solvent, acetonitrile, methanol, hexane, 450. But for water and sodium hydroxide, like the spectra shifted, we had to shift also the monitored wavelength to see the kinetics. And after that, we can say, okay, now we can propose our mechanism. We know the lifetime of the singlet, what we call rate constant of intersystem crossing. The singlet lasts like 2 10 to minus 10 seconds. The triplet is also very fast, 1 10 to minus 8 seconds, which can't be seen. This one can't be seen in nano laser, just in femto, so that you can go to picosecond. So acid-nitro was very slow after this displacement. You have acid-nitro microsecond, neutral one, and acid-nitro deprotonated also in millisecond. It's very, very slow in water. Then from neutral, we just thought about the cyclization of this compound. So it's like we have the oxygen, which was here, binds to the carbon. Then we have kind of cycle, but it's not. When the ring opens, we have nitroso. And then once the living group goes with hydrogen, we have the compound which was isolated. This was the proposed mechanism. After that, we went to the fourth example, which was phenacyl xanthate. We irradiate this compound, as I said before in the second slide. We irradiate this compound, then we saw in propanol, we just recover acetophenone, carbon sulfide, and alcohol, because it was in propanol, hydrogen donor solvent. The same compound we irradiate in acetonitrile, which was not hydrogen donor compound. Then we have recombination of the radicals, which means, okay, this should be radical reaction, because as you know, in radical reaction, we have 3 steps: initiation, propagation, and recombination. So when we saw like acetonitrile, this is like recombination of phenacyl radical. And then this one is also a combination of xanthil radical. I said, no, this should be radical, phenacyl radical and xanthil radical appearing in that reaction. But we have to prove it. So just speculation. Proving that means going to transient spectroscopy to show their spectra, to show their lifetime, and to confirm using different methods like Stern-Volmer kinetics. And then we have synthesized this compound. Phenacyl was very poor. We just methoxy and dimethoxy here to bring inductive effect positively. And then there we have it, methoxy and dimethoxy. After flashing, we got this spectra. Then we said, where is phenacyl radical? And then where is xanthil radical? This was just the spectra we had. But the UV spectra of this compound is not the same as this one. It was about 300, 320, but the transient spectra went until 600. He said, okay, let's take also 2-methoxy. Then we saw the same thing. The lifetime was about microsecond for both. To confirm the presence or the generation or the appearance of the radicals, we had to go and use the radical trap to confirm what they call kinetic Stern-Volmer kinetics, because this diphenylethylene can trap any kind of the radical and then form this radical which is very stable. So what we did, we prepared a solution with different concentration of diphenylethylene with the same concentration of our compound. So as the concentration of diphenylethylene is increasing, we see the data, the straight line, and then we could intercept. We could see the intercept, which is K0, and then the KQ means the quenching, which means the rate constant of the bimolecular rate constant, bimolecular collision. But the K0 is just without any diphenylethylene. That's why you call it intercept. After plotting using different software, as you know, then we got the quenching rate constant was near diffusion control for the methoxy, and then also for a little bit slow for the dimethoxy. But we confirm that there are radicals because they increase, the line increases with the increasing of the diphenylethylene concentration, which actually give the result of bimolecular collision. And then we said, okay, we confirm the radical presence. Now we can propose the mechanism. This is what we proposed. We have a singlet state. From the singlet state, no way to see the triplet state. We just saw the radical. And the radical, the phenacyl radical was about 16 microsecond in acetonitride. And xanthil radical was about 18 microsecond in acetonitride. Then, when propanol is used, here we got acetophenone, and then with other compound. But when it's acetonitrile where we are irradiating, we get this recombination of radicals, which was isolated before we determine the mechanism. So we said, okay, it's fine. We have a complete mechanism. If there is something remained, then we will know. But we have triplet. Its splice time is 0.33 microsecond in acetonitride. But the reaction didn't start from the triplet, just from the singlet after irradiation, we got it. And the last one, the previous one was para-hydroxyphenacyl, but the last one is ortho-hydroxyphenacyl. We took this compound, we used different solvents, different living groups, then we isolate these two. Then the UV of this compound is just the maximum 340, 250, and then it is close to 200. After irradiating in hydrogen donor solvent, we get this. The living group went with proton form acid. The living group can be mesylate, acetate, benzylate, and so on. Then we said, okay, let's try to see the mechanism. If the quinone will be the same, it was in para-hydroxyphenacyl. The quinone here, we tried to protonate. This, you have just the observe the rate constant. You see here is change in absorbance. Observe the rate constant is the rate constant given by the machine. For the neutral one, neutral quinone triplet is about microsecond. Acetophenone itself is about microsecond. And then the deprotonated also becomes very, very long. It's about millisecond because we deprotonate using either 1 molar sodium hydroxide or just water. Then these are the calculated spectra using FT, density functional theory, but depending on time. You see the ionic, the neutral, and the protonated quinone. It was almost in the same wavelength to confirm that this green is for the deprotonated one. And then this blue is the triplet of the normal quinone. We titrate to have the pKa of this quinone. It was not of this compound, not far away from the pK of the phenol. So that we decide to propose, see, like, if you put bed living group, this is the spectra, still 450, and then ionic, the same thing, nothing changed. Once we put like good living group, like mesylate, we have to change because mesylate brings everything in water. And then to add some acid, decrease the pKa in order to have it in neutral form and to avoid protonation. This is what we did. And also here, we have the lifetime of the triplet, which was here. I just put it in the table to summarize what we did here. This lifetime for the neutral is microsecond one. And then for the bed living group, it's the same. Aerated, degassed. In aerated, we have it, aerated solution, we have it 1 microsecond. And then in degassed, it decreases, it becomes slower, which means it's a triplet. What this experiment indicates, like there is a presence of the triplet. That's why in the mechanism, we have to confirm that there is triplet formation. And then the quantum yield of everything. After that, we just proposed the mechanism of saying we start by orthohydroxyphenacyl group. There is a singlet state, the intersystem crossing, then electron state, just proton transfer. There is formation of quinones. This quinone can be neutral or protonated. And then the triplet biradical, which was seen for the para-hydroxy, the previous one, still we're thinking it should be here. And then this is the responsible of the Photo-Favosky reaction that leads us to add this compound in our hand. And then from there, we published in Photochemical and Photobiological Science to confirm our mechanism. And then to end the end of my talk or my lecture is like we can see we are in the same group, but each of us was dealing with each topic and any project. Synthesis, photochemistry of dyes, laser flash photolysis, transient spectroscopy. It was a big group, and then it's still a big group. You can see Dr. Jamal is everywhere, and then myself, I'm here. When I came back, everything was good. Thank you very much. I'm waiting for your questions.
Okay, thank you very much, Prof. Ngoy, for a nice presentation. Who is trying to explain in detail and slowly what is actually the transient absorption spectroscopy and how these tools can help us to propose specific mechanism in organic reaction. So far, the student just know how to understand the mechanism just based on the textbooks or maybe using some computational approach. But we have seen here that there is a tools in laboratory who can help us to prove, to prove the mechanism. But of course, to find out a mechanism, it is not just a single measurement with this kind of tools. We need some proposal how the mechanism should be, and then try to prove with experiments, and then measure on this transient absorption spectroscopy. Okay, maybe this just a brief description about what we have to know about this lecture. So for this session, I would like to invite all the students to ask directly about what you want to know about this transient absorption spectroscopy. It doesn't matter what any kind of questions, because I know this subject is quite hard to understand, especially for the beginner. So don't be shy to ask the question. Okay, please just raise your hand. You can talk in Bahasa or in English directly, or you can also try to type in the chat box. Is there any question? Okay, Shahrul. Okay. Yeah, there is 3 questions. Okay, I will try to uh, read the first one. This is from 5. He want to know, okay, yes. This is about the role of the solvent in this kind of photochemistry reactions. Should we really consider the role of the solvent in this kind of photochemistry reactions, especially when we want to prove the mechanism? Probably you can directly answer the first one before we continue to the second question.
Okay. When we are thinking to propose the mechanism, just to speculate before the proof, you need also to think about the solvent properties. There are solvents which are hydrogen donor. There are solvents which are not hydrogen donor, and they are working differently. The hydrogen donor will just try to set up the hydrogen in the compound, and which will change the mechanism. The non-hydrogen donor, like acetonitrile, hexane, and other one. There are also solvents which are acid, which the pKa is like 15, like methanol. Using that one also, it's not hydrogen donor, but you have to take care about the mechanism, because the methoxy can be formed during the reaction. So it depends on the solvent. You have to take care of the solvent.
Okay, 5, is it clear? I think it is clear, right? Okay, we can move to the second question. It is from Shahrul Febrian. Sorry. From Shahrul. Yeah. Yes. This is from Shahrul. To find out the intermediate using this transient absorption spectroscopy, can we set these tools to find out only one intermediate in one measurement, or can it also detect many intermediates, which is probably formed during the reaction?
Yeah, it depends on the time scale. As I said, the time should be shorter than the laser beam. So if you set the shortest time, you will have the first intermediate, which is shorter. The lifetime is short. But if you set the intermediate time where you can see both, it's also fine, but you won't see both in a maximum. One will start disappearing, and then the other one will start coming, or the reverse way. And if you push in longer time, you will not see the shorter one. You will just see the longest. So it's a game you have to play with the time. That's why you see in my spectra, I used to write, for example, 9 nanoseconds after the flash, 220 nanoseconds after the flash. You see the difference. In 9 nanoseconds, the shortest stuff will come out, but the longer one is not there. But when you are pushing to 10, 20, maybe 100, the previous one will disappear, then you get the new one. So if you set up the time which you can see both, it's fine also, but it's very rare.
Yeah. Okay. Yeah, it is clear that each intermediate has their own lifetime, which is quite distinctive each other. So it is hard to, let's say, to just find 2 or 3 intermediate directly just in one measurement. Okay. And the next is, okay, this is from Afri. First, it's about I want to ask about the challenge of using this spectroscopic method and how can it be used to help determining the structure. Can it be helpful to elucidate the structure? And what is the challenge to use these tools? Maybe that is the first question.
Yes, these tools are called in other way kinetics tools, and in our country we used to call it fast kinetic course lecture. Is a fast kinetics. So in kinetics you don't need the structure. You know, kinetics means following the disappearance of the compound according to the time, the concentration with time. So there's nothing about the structure. The formation is taking how long? The disappearance is taking how long? You start from the reagent to the product. What was in between, and then in what time? This is the problem. It doesn't depend about the showing the structure. No, this is just for kinetics.
Okay. Yes, Afri, again, is that as we mentioned before at the beginning, that this is about the kinetic tracing, right? And then if we are talking about how is the mechanism can be described, that we have to understand the mechanism and then propose how is the mechanism and then prove with the tools. So by using these tools, actually, we can find out the kinetic informations in particular. And then, of course, to help us understand what kind of intermediate finally, which involved in this reaction mechanism. Okay, I think that's the first one. And then the second one, regarding the use of solvents, are there any provisions for selecting the solvent use? From the previous presentation, why do sodium hydroxide and water solvents have small values and slow speeds in the proof of the Ac-nitro intermediate?
Yes. Okay. Ac-nitro was published before, and then with other compounds, and then they said, in the literature, they said, to prove the presence of Ac-nitro, you have to do pKa titration until you deprotonate the compound, and then you flash the deprotonated solution to see where it absorbs in transient. If it's redshift, then this is Ac-nitro, the titration. So to deprotonate, I need to know first the pKa of my compound, which was almost 10.5. So to deprotonate, I used to put water or basic solution, which can deprotonate in that solution. So I prepared just 1 molar solution, and then the slower comes from the bonding between water and the compound. The non-hydrogen donor, like acetonitrile, for example, for the case, just speed up the reaction. But water, you know, the dielectric constant of water. is almost 80. So water is having like two properties: to dissolve the compound and then to dissociate the compound. This is the power of water according to epsilon, dielectric constant. So that's why this property is slowing, it's making the reaction very slow, lowering reaction. This is the way. The same thing with sodium hydroxide, which is dissolved and prepared in water again. I guess I responded.
Yes. Okay. Thank you for the answer. And the next is from Jobin Armando Hutafea. So if it is regarding the material, I will share the recording because it is live stream on the YouTube, and then I will share later on the link. And then the next is about what is the role of transient absorption spectroscopy in revealing the complex organic reaction mechanism that are difficult to understand with other techniques. Can be it helpful for this kind of complex reaction mechanism?
Yes, I think there was a slide talking about, first of all, this one, time-resolved spectroscopy versus steady-state reaction. So the steady-state reaction is related to complex reaction in kinetics, which have many steps. And then each step is having its own rate constant and its own time. It's like you start from singlet is a step, triplet is a step, biradical is a step. Combining all of that, this is complex reaction. So it's kinetic
Yes.
of one.
Yeah.
That's the point.
Okay. So what is the common difficulties to resolve this kind of problem in complexity?
Sorry again?
I mean, what kind of difficulties? Maybe in point of view, the technical problem during the measurements.
Yeah. There are compounds which are not giving good signal. So you can fight to have a signal to you will change different mirrors, different device to have a signal, and you don't have. So you have to change the machine or to prepare another solution. You can fight all day. You didn't see any signal in laser. But there are also compounds which gives good signal, and then you can study it very good. That's why I was talking about bad living group and then good living group. The good living group, you will not suffer. You will get good signal. I guess when students will have this lecture on their hand, they will see in different spectra, the change in absorbance are not the same. There are compounds which absorb very much, and then the other one, just nothing, 0 point something. We are just forcing to generate the stuff. It's very difficult to generate the compound which are not able to give the signal.
Okay. Maybe the next is about the interpretation of the result of measurements. So what is the difficulty to interpret?
Yes. If I try, for example, to get the spectra NE, then I will explain. I see, for example, this just is like a signal, it's nothing. How can I say this is triplet and this is biradical and this and this? There are some experiments which are done in other side. For example, to prove the triplet, I have to use the aerated solution and to use the degassed solution. The aerated solution will have short lifetime because of the oxygen, will catch everything in that, knowing that the oxygen is the only compound, the only atom in the periodic table, which is in excited state. In ground state is triplet. So the oxygen will just quench the triplet, so it will be very slow, very short. But if I degast, I remove all the oxygen, the triplet will be longer. If I see the difference between aerated and degast, I can confirm in that place this species is triplet. To confirm the radical, I showed you the Stern-Volmer slope, straight line. So I have to prepare solution in other side to flash, to get the kinetics, then to plot in the computer to see the intercept, and then the bimolecular rate constant. So there are sensitization, for example. There are many experiments which are done to confirm what we see in the machine. I can cite degast and aerated solution, quenching and sensitization are enough, trapping also the radicals. They are enough to confirm and to interpret our result.
Yes, I think it is also clear that we can't just interpret a single result obtained from this tool, but we have to do some cross experiments, maybe
Yes.
with different technique also. So in order to confirm what we suggest as the mechanism. Okay, the next is from Hebelina about the limitation of this method in determining the mechanism. Is there any limitation compared to probably other methods?
Yeah, this is what I said. You can have in your laboratory, you have just femtosecond laser, but the intermediates are coming out, are generated in nanosecond. You will not see anything. If you have both of them, like we had micro, milli, nano, and femto, but the compound, the species is just faster than all your setup. You won't see anything. This is the very limitation of this method. You have to have compounds in between this range. But if you have all the devices, but they are very slower than all you have, no way. If they are very fast, then all you have, you are limited. No way to see and to predict anything.
Okay, that's clear. The next is from Septi. This is about the accuracy of the measurements. How good is the accuracy of these tools to measure some things? Let's say this is kind of determining the kinetic.
Yeah.
Is there any percentage or something, deviation?
Yeah, if you can see here, when I was doing kinetics, you can see error bars.
Yeah.
Strength rate constant, you can see in that plot there are error bars. So it's like I'm not doing just once. I used to do 3 or 4 times. So to get the mean, the error bars, and then to get the intercept and then the slope. So just one flash can give you one kinetic. Then the other one will give the other kinetics, which may not be the same, but they will be similar anyway.
Okay. Okay. The next is about the applications of the tools to investigate the mechanism in water media, because it was mentioned before that the reaction in the water is slower compared to the organic solvent. So is it possible to do this kind of investigation, let's say for biochemistry reactions?
The reason we are trying to shift with water is like we want to go to a human being. This is the reason we are trying to use a phosphate buffer or water himself, just to have it in that case, of physiologic state for human being. But organic solvent can be used if the compound is not soluble. But we are trying to move to water soluble because we are trying to have medicine and then to help biochemists to do their job.
Okay. Next is from Azrina. This is about the low intensity of the signal, probably from the absorptions obtained from the instruments. How can we increase this kind of signal? Whether we have to increase the concentration or different solvent or anything else in order to get better signal, like especially when we have really low absorptions?
Okay, if the compound is not giving good signal, first of all, you have to check to increase the intensity. And you have to make the setup very well. But be careful by increasing concentration, because you will have the triplet annihilation. So
yeah.
don't increase the concentration, you will have a problem with triplet annihilation. But just try to move the setup and then to increase the intensity of flash so that we can generate which was hidden. I can't advise people to increase concentration because they will give wrong spectra and the wrong result.
Okay, probably this is the last questions because we have a limited time. This is from Rahul Vikranza. So what he want to ask is about how does transient absorption spectroscopy with its ultra-fast time resolution surmount the impressive of probing transient intermediate in organic reaction mechanism? And what are the current limitations and future prospects in achieving unprecedented precision and deep in understanding complex molecular dynamics?
I don't
Okay.
understand. It was going kind of too long.
Yes, probably first is about the uh okay, just let me see. Yeah, probably the previous one is similar from we have before, but uh what are maybe this is really important for the future perspective. What is the limitation of the tools? Can these tools survive to challenge any more complex problems in the future in understanding the reaction mechanism?
Yes, as I wrote here, the point of having this, what chemistry needs to, why chemistry need to have this lecture. The first reason is like we have to identify the intermediate. So the challenge is if you are not able to identify the intermediate, you will just speculate without any proof. But if you are able to generate and identify the intermediate, now you can continue your doing whatever you want to prove, and then to show the lifetime, the disappearance, and everything. Also, you can assess the mechanism of reaction. This is the problem. The reaction mechanism can be assessed by just detecting what we call distinguishable reaction intermediate. But the limitation, as I said before, is like there is no signal in all wavelengths, and using all devices, we faced those kind of compound which didn't do anything. But if you know that there is nothing coming there, but you may generate this compound, what we used to do what we call sensitization. You just put the sensitizer with the compound together, but the compound is not seen. You are flashing now in the sensitization place. The sensitization is transferring the triplet energy to your compound. If the compound go to triplet state, even if it doesn't have the signal, because it gets more energy from the sensitizer, it will come up. As you are flashing, the sensitizer is going down, your compound is coming up. You can see and generate the triplet. This is the way, but the limitation is just if nothing is seen, you try by any way, just forget.
Okay, thank you very much again to Prof. Ngoy for insightful lecture today. And I think all students hopefully can understand and recognize this kind of tools, especially for investigating the organic reaction mechanism. And for that reasons, I would like to remind all the students that you have an assignment to make a summary about what was the lecture today. Okay, maybe this is the end of our lecture, but before we close the lecture, again, I would like to thanks to Prof. Engoy who spent a time with us here and deliver some nice lecture. And we hope that you can join with us again in another occasion and probably in different topic also. Okay, probably I would like also to share with Prof. Engoy. Probably could you please stop the share screen? I would like to share something for you.
Okay, I don't know how to share.
Okay, just a minute.
Is it fine?
You can just let me see. Ah, yeah. At the top, maybe you can see the stop share screen.
Plus,
Just a moment. Can you find the menu?
yeah.
Just a minute. Okay. Anyway, if it is difficult to find out the stop sharing, uh, actually, I would like to take a picture with all of the audience.
Yeah.
Uh, yeah, but moment maybe if it is possible to close the share screen, it would be nice to have all the students or the audience in the screen. Ah, okay. Now that's good. Okay. Probably before that, I would like to share something for you. This is just an appreciation from. Can you have a look to the screen?
Yes.
Yes. This is
Thank
just a
you.
little appreciation from our Dean of Faculty Mathematics and Natural Sciences. The certificate for this guest lecture to Prof. Ficho Engoy Colombe
Mhm.
for the guest lecture today.
Thank you very much.
Okay. Yes, I will send you this letter. And then now probably I would like to have all of you to open the camera and then we will have some picture. Please, all the students, just switch on for a moment the camera and then we will have the picture. First, I would like to pin our guest lecture and then to have the screenshot. Okay. And now is the first page. 1, 2, 3. Okay. And the second one. 1, 2, 3. Okay. Once again, thank you very much, Prof. Engoy, for joining with us this afternoon here. I hope you are not mind to come again. Maybe someday you can come and visit us here in Indonesia. Thank you very
No
much
problem.
and see you next time. Bye.
Okay, thanks, Dr.
Assalamualaikum
Jamal.
warahmatullahi
Bye.
wabarakatuh. Bye.
Bye.
Thank you, Prof.
Thank you, Prof.